Hi everyone, welcome to our live seminar for your first physics exam. So the goal for tonight is to go through everything that you could potentially be asked on your exam paper tomorrow. Now, this is OCR Gateway, but there is overlap with AQA on the topics that we'll cover as P1 and on P3. So when we get to P2, then you can just shut your brains down for a bit if you're doing AQA. Now, obviously, I do have the chat window open, but as we found over the past couple of live seminars, that if you're going to fill it with a load of random rubbish, then I generally just don't bother looking at it until later when I block those people. So if you've got questions, post them in the actual chat window, because that means I can then see them and hopefully respond to them for the end. If you don't have any questions, then don't post things in the chat window. It's quite easy. Right, we are going to start off with P1, which was all about atoms to start with. So the good news is that if you learned the history of the atom for your chemistry, then the good news is it's the same in physics. So you've already got some of this learning hopefully locked away from the other day. There are 4 scientists you need to know. First of all is Dalton. He was the one that had a look at these atoms for the first time and said, you know what, these are tiny indestructible spheres. So he said that all atoms in an element are the same, and that the atoms in different elements are different from one another. Second scientist is Thomson. So Thomson is the one who used those cathode rays in order to actually investigate what was going on with hot metals. And he discovered that they were made from these little negatively charged particles called electrons. So he came up with this idea about the plum pudding model in order to explain that neutral atom. So a positive cloud with these little negative dots around it, like the plums. The next scientist that we've got is Ernest Rutherford, and he was actually looking at alpha particles and firing them at gold foil. So what we actually saw there was if the plum pudding model was right, they'd have gone straight through, but they didn't. Some of them actually bounced back and reflected at different angles, and so that didn't work. As a result of that, he suggested that atoms have this tiny positive nucleus surrounded by the electrons, and that most of the mass of the atom is found within the nucleus itself. And that then explained why those alpha particles bounce back. Scientist number 4 is Bohr, and he then said that the electrons only move in these fixed orbits or electron shells. If you're doing AQA, you do need to know the 5th scientist, which is Chadwick, and his discovery, which is the neutron. So OCR folks, you don't need to worry. AQA, Chadwick discovered the neutron. In terms of the size of our actual atom, then that is 1 × 10 to the minus 10 meters. So just remember that as its actual diameter, 1 × 10 to the minus 10 meters. If you're looking at the radius of the nucleus, that's even smaller, as obviously it is just part of the atom there, and that comes in at 1 × 10 to the minus 15 meters. And hopefully we remember our good old structure of the atom. So the nucleus in the middle there, made up of our protons and neutrons, and then the electrons in these orbitals or shells around the outside. So hopefully we do remember the basics of the atom from our chemistry the other day. Next thing we need to come on to is density, which is also one of those practical tasks they could ask you about. So when we're talking about density, quite simply, it's how much mass there is in a given volume. So what we actually find is our first equation that we need to know comes up here. So density is the mass divided by the volume. Now, what you need to look out for here is that mass is in kilograms. One of the little tricky things they sometimes do on these papers is they'll give you a mass in grams, not kilograms. So remember to convert first of all. So anytime that you actually see a mass in grams, divide it by 1,000 to get it into kilograms. Once you've got the mass in kilograms, divide that by the volume, and you've got your density. Obviously, remember, you can use the triangle method if you need to rearrange it, but you can rearrange just using maths if you're good at that side of things. In terms of the practical that they talked to you about with density, then you've got a couple of options here. The first one is for those regular shaped objects, so your squares, your rectangles, where hopefully you know how to work out the volumes from maths, so length times width times depth, and then you'll get your mass. So you can just use that one. If it's, however, an irregular shaped object, so a lump of plasticine, a rock, anything else that's a weird shape, then first of all, we need to get the mass, use electronic balance for that. And then we use something called a Eureka can to actually get the shape of our irregular object as a volume. So what you do with your Eureka can, which is basically like a beaker with a spout off the side, fill it all the way up with the water first of all, and then you place a measuring cylinder under that spout. As you then carefully place your irregular shaped object into the water, it displaces the volume of water that's the same as the volume of your object. So you just read it off the side of the measuring cylinder, and then you've actually got the total volume of your object. You can then use that in mass divided by volume to get your density nice and easily. Now, when we've actually done density, we need to understand a little bit about how this works in terms of solids, liquids, gases, and so forth. So what we actually find then is that in a solid, we've got more particles in any given volume than we do in a gas. So it has a higher density. So more particles is a greater mass and therefore a greater density at that point. And do remember that when we're actually looking at density, there's a couple of things it's dependent upon. First one is the arrangement of the particles, and the second one is your mass of the particles. Because do remember that obviously density is mass divided by volume there. While we're talking about mass, then we do need to remember this law of conservation of mass. So that quite simply is just that particles are neither created nor destroyed. So if we start off with a kilogram of ice and we're going to melt it, then we're going to have a kilogram of water. If we evaporate it, we've got a kilogram of steam. So each time we've still got a kilogram. We're not destroying particles. All we're doing is changing their state. So that's just conservation of mass there. Next thing we need to understand then is a difference in terminology that we tend to just kind of use interchangeably. So the first word we're going to have a look at is temperature. So when we're talking about the temperature, quite simply, that's how hot or cold something is. So this is what we're going to use a thermometer to measure. So its units will be degrees Celsius or Kelvin, and it's going to tell us about the average kinetic energy of those particles. The other option we've got is obviously heat, which is all about energy. So it's the energy in the thermal store at that point. Because it's energy, it's measured in joules, which is given the symbol of a capital J, and this is going to depend upon the arrangement of the particles and how fast they're moving. If we've got an object and we heat it up, then what we actually find is there's three things that could happen. First of all, we can change the energy stored in the system and increase the temperature. Secondly, we can produce a change of state, so it goes from solid to liquid or liquid to gas. And we could also make chemical reactions take place. What we're looking at there then are two potential changes. The first one is a physical change, which quite simply is just the change in state. So that would be your solid to liquid, it would be dissolving. And the key things about this is we've got no new substances being made, and they're usually reversible. If we think about the chemical change, then as the name suggests, we've got a chemical reaction taking place. So we're making new substances, and it's usually irreversible as a result of that. So make sure you do know the difference between the physical and the chemical changes there. The next thing we're coming on to is another one of these practical tasks that you need to know about, which is specific heat capacity. So specific heat capacity is the amount of energy needed to raise the temperature of 1 kilogram of a material by 1 degree Celsius or 1 degree Kelvin. So the units for it are joules per kilogram, degree Celsius or Kelvin, depending on which measurement of temperature you are using. Now, there are three things that this is going to depend upon, okay? The first one is the type of material you've got. The second is the mass of material. And the third is the actual temperature rise that you are trying to do. So what we actually have here is an equation that's given on the good old formula sheet. So you're going to get one of these tucked inside your exam papers tomorrow. And what we'll actually find is that you've actually got your first equation at the top here. Okay, so this is for your specific heat capacity questions. Now, you don't have to memorize it. It's given to you in the exam, one of those nice ones finally. So what we're actually going to be doing with this is looking at an experiment that you probably did with either a big metal block or some water in a beaker surrounded by some insulation. So what we actually have here then is we've got our thermometer, obviously, because we're looking at a change in temperature. We've got a little electric heater over on this side that's then connected into our power supply, and we've got our material that we're investigating. Around the outside, we do have insulation here, which is obviously to minimize any of the heat losses to the surroundings. So when we're looking at this one, because it is one of those practical tasks they can ask you about, there's a few things that they could put on that make it so it's not as accurate in its results as it could be. So a couple of key things to look out for is that in the heater here, if whatever substance it is actually sticking outside here, so if we've only got it here, say, so the top of the heater is still sticking out, then that's a potential source of inaccuracy, because some of the energy going into the heater then isn't heating the actual material. So look out for bits like that, because that's a really easy way to then be able to say, here's a problem, and therefore we can fix it by making sure it's completely covered. If it doesn't have insulation around it, then you could talk about putting the insulation around the outside to then minimize the transfers to the actual surroundings there. So just think about some obvious bits like that. When we're talking about the specific heat capacity then, is that if we've actually got an object with a high specific heat capacity, then it's quite resistant to changes in temperature. So a really good example of this is things like water, for example. Whereas an object with a low specific heat capacity is going to heat up quickly. So if they're going to ask you about what material you actually should use for a saucepan, then you want one with a low specific heat capacity, because that means it's going to heat up nice and quick, therefore cook your food quickly. You don't want to pick the one with a high specific heat capacity, because that's going to take a lot longer to then heat up. The next thing that we come on to then is specific latent heat. Now, hopefully we do remember these bits back from year 7. So we've got solid, liquid and gas, and then we've got the names of the processes that change between them. So solid to liquid is melting, liquid to solid is going to be solidifying or freezing. Your solid to your gas is subliming. Your gas to your solid is deposition or depositing. Gas to liquid is condensing, and then liquid to gas is vaporizing or boiling. So you do need to know those actual changes, the names of the processes, so that you can identify them first of all. They could also ask you to talk about this little graph here. So this is just showing us what's actually happening to the temperature when we're actually heating it up over time. So at the beginning, we can see it starts off at -80, and we've got the ice warming up. So it's solid ice all the way until here, where we get that flat line, the plateau. So where it plateaus here, what we're actually seeing is that all of the energy going into our substance is actually being used to break the intermolecular forces that are holding the molecules together in that nice regular solid arrangement. So what we actually find is it doesn't increase in temperature here, because all of the energy is going into breaking those intermolecular forces. Then as soon as it's turned into a liquid, we see the increase again in temperature as the water is heating up. When we get to the second plateau up here, then again, intermolecular forces are being broken. So all of the energy going into our system then is breaking those intermolecular forces between the particles in the liquid to change it to a gas. So just remember those key phrases there, okay? So breaking intermolecular forces to cause a change in state. That's why we've got that plateau, that flat part of the graph there. When we're talking about the specific latent heat, there are actually 2 types of latent heat we could talk about. You've got the specific latent heat of fusion, which is the energy transferred when 1 kilogram of a substance changes from solid to liquid or from liquid to solid. And then we've got the specific latent heat of vaporization, which is the energy transferred when 1 kilogram of a substance changes from the liquid to the gas or from gas to liquid. Now, this one again is given to you on our little data sheet, second equation this time. So it's just your thermal energy is mass times your specific latent heat. The way that they can make this question a little bit trickier is by giving you a table that's actually got a range of different materials, and then you'll have the 2 columns, the specific latent heat of fusion and the specific latent heat of vaporization. So you need to read the question here in order to actually pick out what is the change in state first of all, so you know whether it's fusion or vaporization you need, and what material is it. As soon as you know those, just follow the table along to the right box, use that, times it by the mass in kilograms again. So that's all you need to do in order to get those marks. One thing I will say at this point is remember to take a calculator tomorrow, because not all schools have 1 million calculators to loan out to you. So take your own calculator and you can use it to actually work it out. And don't forget as well to show you're working, just in case you mistype a number, then at least you're going to get some of the marks, even if it's not all of them. Next thing we come on to is pressure then. So the first type of pressure we're going to look at is pressure in gases. So if we think about when you blow up a balloon as one of the common examples here, then when you're actually blowing into the balloon itself, then you're increasing the number of air particles inside that structure. So as the particles then collide with the surface of the balloon, then they create this tiny little force each time. And those collisions are what create that gas pressure, and therefore the balloon expands. If you add more air particles to a container that can't expand, so a rigid container, then the pressure is going to increase. And obviously, if you increase the pressure too hard, then it's going to actually explode, okay? Do remember that if we increase the temperature of a gas, then the particles are going to gain kinetic energy, so they're going to whip around a lot faster. That means they're going to be more frequent collisions with the sides of the container, and therefore the pressure also increases. So two ways to increase the pressure: more particles going in, or we can increase the temperature, okay? When we come to actually measuring pressure, then quite simply, you use a pressure gauge. So the units for pressure are pascals, which are given the units PA, capital P, lowercase a. And what we'll find is they could use a kilopascal, which is just 1,000 pascals. As always, where we see the word kilo, just 1,000 times bigger than the other unit. If we decrease the pressure, then the pressure decreases. I think I said that wrong. Let me try again. If we decrease the temperature, then we decrease the pressure. So that if we were to theoretically cool a gas down to absolute zero, so 0 degrees Kelvin, then we would have 0 pascals of pressure. Now, we don't generally manage to do this in a lab for obvious reasons, but we can work it out, because you can obviously work out the pressure of gases at different temperatures, which are easily achievable in the lab, plot those on a graph, and then you can just extrapolate, so just extend that line to get a pressure that's not easy to recreate in the lab setting. For those of you doing GCSE physics, then you need to listen to this bit. If you're doing combined science, don't need to know this bit, so you can shut your brains off for a few minutes. So for those of you doing the physics, then you need to know about the relationship between pressure and volume. So when we're looking at this, pressure and volume are inversely proportional. So that means that if we double the volume, then we halve the pressure. Now, go careful with some of these phrases where we're talking about relationships. So if they were to say, what happens to the pressure if the volume doubles, you can't just say it decreases. It's not enough. You've got to give the specifics, so it's halving, okay? So just look out for those phrases where they're using things like doubles, halves. You need to use a similar term. What we actually find is that in this scenario, the collisions of the gas particles, they're producing this force at right angles, so 90 degrees to the surface. So that if we then halve the volume, then there are going to be twice the number of those collisions at right angles to the surface every single second with the container. Particles are still moving just as quickly, so they're going to collide a lot more frequently if there's less space, so there's less volume for it. Now, the next thing we need to understand if you're doing higher tier physics is all about how we can increase the internal energy of a gas. Two key ways we can do this. First one is by heating it, and the second is by doing work on it. So basically, the good example of this one is the old bike pump, where you're pumping up the tires on your bike using one of the little hand pumps. So when we apply the force onto the pump, then the gas is going to get hotter. If the gas gets hotter, the kinetic energy increases, so the particles are moving quicker, and therefore there are more frequent collisions with the container, and the pressure then increases. So obviously, just remember that side of things. For GCSE physics candidates, foundation and higher, you need to know about atmospheric pressure. So the Earth itself, our lovely planet that we all live on, is protected by the atmosphere, just as well, because otherwise we wouldn't live. Now, the atmosphere itself is just this layer of gas that covers the Earth up to a height of about 700 kilometers. And depending on what book you read, will give you a slightly different height on that, depending on where they're going. But the key thing there is that all of these gases that make up our atmosphere are going to be exerting a pressure. And that's what atmospheric pressure is. It's the pressure of all of the gases that make up our atmosphere pushing down on us little entities here on the ground. And if we're on the surface of the Earth, then we're looking at atmospheric pressure about 100,000 pascals. You don't have to memorize that number. It's just to put it into a bit of context here. Now, if we think about a good example of something you hopefully saw in your lessons of the collapsing can experiment. So you've got a normal drinks can, and when it's open, then we've got equal forces in all directions. So the can just sits there, doesn't do anything exciting. It is merely an open can that is not changing shape. If, however, we remove the air from the can, then it collapses. So you probably saw that example where your teacher took the can, dunked it into the bottle, into the big bowl of water, and then the can crushed itself down. What we actually find then is that the reason it does that is that if we've actually removed the air from the can and we've got our atmospheric pressure around us, then there's atmospheric pressure is greater than the pressure pushing out, and therefore it collapses. If we think about moving away from the surface of the Earth, so going up into the atmosphere a little bit, then atmospheric pressure is going to decrease. The further up from the surface you go, then the lower the atmospheric pressure will be. And the whole reason for that is that there are fewer particles of air pushing down on you. Now, what you'll find is if you're using a pressure gauge, then it's not going to read 0 when you first turn it on, for the simple fact that it's going to be registering the pressure in the atmosphere around you. So just remember that little fact about our pressure gauge. For those of you doing higher tier GCSE physics, then we need to know about the liquid pressure. So what we actually find is that water is going to exert a pressure called liquid pressure. Because the water molecules are close together, then they collide with each other. They'll collide with containers, they'll collide with anything at all in the water. And liquid pressure, in a bit of a difference to our gas pressure, acts in all directions. So gas pressure, remember, right angles to the surface, liquid pressure, all directions. Now, the pressure in our liquids is going to increase with depth. So the lower down you go in the ocean, then the greater pressure gets. For the simple fact that the further down you go in the sea, then there's more particles above you pushing down, so greater pressure. We'll also find that if we've got a denser liquid, then we'll have a greater pressure. So remember, if you've got water and something much denser and you're at the same depth, then the denser liquid will have a greater pressure, just because we've got a greater weight of liquid in our denser liquid pushing down. Now, one of the things that you could be asked to do here then is to calculate the pressure in a column of liquid. So what you'll actually find is on your little sheet here, going down to the higher tier section there, that you can see pressure due to a column of liquid is the height of the column times the density of the liquid times G, which is gravitational field strength. So it's on your formula sheet, just remember to use it. Last thing that you need to know on the higher tier for the physics here is all about whether things float or sink. Now, items are going to float if the upthrust balances the weight. Hopefully, we do remember our equation for pressure, which is force divided by area. And when we're then looking at this, we need to know about how we can have these objects that float at different heights. So things like a submarine, for example. So submarines don't just sit on the surface, or they don't just float halfway down in the ocean. They can change where they're floating. And the whole reason behind that is that in their structure, they've got these tanks around the outside that you can either fill with air or water. So what we actually find is that if you fill them with water, then what you're actually doing there is you're increasing the mass, and therefore you're going to be changing our force. So what we can actually do is make it float lower down in the ocean, so you can make it sink deeper. Whereas if you want it to rise to the top, then all you do is you push air into those tanks, forces the water out, and then we're changing our actual height. That's all of P1. So those of you doing AQA, P2 is irrelevant for you on paper 1. Those of you doing OCR Gateway, then P2 is our next topic. Now, obviously, I am keeping an eye on the chat there, and it's really helpful if we could avoid doing things that mean I have to stop and then remove people and block you on the channel, because it just wastes our time. So you want to make silly comments, go somewhere else, or maybe open a book and revise for your exams tomorrow. So first thing we need to know about then is speed. So speed is hopefully something we've already learned in maths as the equation. You may even have used it today. Now, when we come to measure speed, there are two things that we need to know. We need to know the distance, we need to know the time. So what we actually find then is that when we're looking at the distance, we use a ruler, okay? If you're measuring time, then you're going to use a stopwatch in all instances. Obviously, one of the things that you could do is use a light gate, which is actually a better, more accurate time measuring device. So if you're given an experiment where we are measuring speed for any reason and they've said that they've used a stopwatch in the method, ask you for an improvement, use light gates is always a good one to go with. Now, in terms of actually measuring the speed then, once you've got your distance and you've got your time, then speed is distance divided by time. That's one of the ones that you need to learn for your exam. Now, if it's uniform motion, that means the speed doesn't change. So it's just traveling at one speed consistently. If, however, it's non-uniform motion, then the speed is changing. So in order to work that out, it's an average speed that we are getting, because remember, the speed will change over that time period, but all we're doing is looking at the total distance traveled and we divide it by the total time it took. So it's an average speed if it's non-uniform motion. There are a couple of important things that you need to know here in terms of the measurements. So the first one is a kilometer is 1,000 meters. The second one is a mile is 1,609 meters. And the third one, an hour, is the same as 3,600 seconds. Now, obviously, you can work out the hour in the exam because hopefully we know that there's 60 minutes an hour, 60 seconds in a minute. So you can just do 60 times 60 to get the 3,600. So just bear that one in mind. Now, in terms of vectors and scalars, these are two terms you need to know. So a vector is a quantity that's got both direction and magnitude or size, and that would be things like forces. So what we do here is we're going to use an arrow, and obviously the direction that arrow is pointing in shows you the direction it's acting in, and the length of it is going to show you the magnitude or the size of it. If we're talking about a scalar, then what we're actually looking at in that case is something that has a magnitude or a size, but no direction. Okay, so scalars have a size but no direction. Vectors have direction and size. If we think about a good example then of distance and displacement, the distance is how far you've traveled, irrelevant of what direction, so it's a scalar quantity, whereas displacement is the distance from a point in a particular direction. So that then means that it is a vector because we've got both a size and a direction. And just remember, when you're talking about displacement, then you'd actually put down something like 4 miles east, okay? So you would actually have that kind of direction put in there. You could also put it as pluses or minuses, but there will be some kind of direction here. If we're talking about speed and velocity, speed is the scalar, velocity is the vector, because the velocity is how fast it goes in a certain direction. Now, that is important when we then come on to have a look at some of these other concepts. So what we need to look at next then is acceleration. So acceleration is another equation you need to know, which is the change in velocity divided by time. So hopefully you've learned that one. And when we're calculating acceleration, you need to know, is it positive or is it negative? So if we're increasing in velocity, then it's positive acceleration. If it's decreasing in velocity, it's negative acceleration. And you can just give that a plus or a minus sign to show that. If you're talking about an object that is falling, and I'm pretty sure they had one of these questions on there last year, then we've got acceleration due to gravity. Now, acceleration due to gravity, if you're being very particular, is 9.81 meters per second squared, or 10 meters per second squared if you're being a little bit less specific. So just remember, acceleration due to gravity, 9.81. Next one that we come on to is, again, something I believe you've done in maths, which are distance time graphs. So you obviously need to know what's happening in your distance time graph. First and most important thing, look at the label on your y-axis, because we're going to have a look at both distance time and velocity time graphs, and the key difference is down to what that y-axis says. That's then going to change what those lines mean. So on this one, if we've got a horizontal line, then it means the object is stationary first of all. So you can see here we've got a horizontal line, so therefore the time is increasing, the distance stays the same. The object isn't going anywhere. If you've got a diagonal line, then the object is moving at a steady speed. If it's a curved line, then it means it's moving at a changing speed. And if you need to work out the speed at all, it's just the gradient of the line. So if they wanted you to work out the speed of this part, all you do is you'd work out, obviously, the difference in your time, the difference in your distance, and then do distance divided by time. And then you've got your speed there nice and easily. If obviously you are looking at the distance time graph, then that's going to show you the total distance traveled. So all you need to do for that is just read off where it comes to at the end of the line. That's your total distance that you've traveled. If they gave you a displacement time graph, then what we can see here is you could have either a positive, 0, or negative gradient. And the gradient there is velocity, because it's got this direction associated with it as well. When we come on to our velocity time graphs, then what we have are obviously this ability to have both positive and negative on here. So you do need to remember that sometimes they will have both positive and negative values on there based on the velocity itself, because it has both magnitude and direction, remember. Now, as I've said, the key thing you're going to look at is the y-axis. Because if it says velocity, then we've got velocity time graph. If it says distance, it's a distance time graph. And what we can see is that these lines that we had the same on the other one actually mean different things. So first of all, that horizontal line that we had, which previously on our distance time graph said it wasn't moving, in this case, it's moving at a constant velocity. So in this case, it's traveling at 8 meters per second for that entire time. When we've got our diagonal line here, then that's a constant acceleration because it's increasing. If we've got the negative gradient, then it's a constant deceleration, it's slowing down. And again, if you've got a curved line, then it just means it's a changing acceleration. So you need to know the difference between what kind of graph you've got and therefore what it means. If they actually ask you to work out the distance from a velocity time graph, you just need to work out the area under it. So what we're actually doing here is, you can see, if they were to ask you to work out the area here, then you're probably looking at that and thinking, how on earth can I work out that weird area? And the answer is split it up into shapes you know. So divide it into one triangle here, a rectangle in the middle, and another triangle on the side. You can then just use your maths knowledge to work out the area of a rectangle, the area of each triangle, and then add it together. And that then tells you the total distance that is traveled. Now, the next thing we come on to are the equations of motion. Now, one of these is actually just looking at the final velocity squared minus the initial velocity squared is 2 times the acceleration times the distance, which is right here. So you don't have to memorize that one, which is nice because it isn't half a mouthful. So obviously, if they're giving you a question to do with initial velocities, final velocities, accelerations, and distances, go to your data sheet, use that, substitute in. The next one is one you do need to know, which is all about kinetic energy. So kinetic energy is 0.5 times the mass in kilograms times the speed squared. So make sure that you know that equation and don't forget the squared on the speed. Because it's kinetic energy, then that means the units for it will be joules. And what we're looking at here is something that's moving. That's generally kinetic energy, it's movement energy. So make sure that you can use that. And again, because we are talking mass, it's kilograms again. So if you've got something given to you in the question in grams, divide by 1,000 to get it into the kilograms and then substitute it in. Remember to show you're working and to use a calculator to work it out. The next bit we're coming on to are good old Newton's laws. So the first one that we're going to look at, oddly, is Newton's third law. And that quite simply states that Newton's third law is for every action, there is an equal and opposite reaction. So what we have are pairs of forces. So we've got these things called an interaction pair. So each force is acting on a different object. The forces are the same type and size, and they're acting in opposite directions. That's what we mean by an interaction pair. So basically, it's the opposites, if you like. Now, what we're looking at here are two kinds of forces. We've got non-contact and contact. So non-contact forces then are the forces which are produced because an object is in a field. So these are the ones, as the name suggests, that don't need the object to be in contact with something for a force to occur. So this could be things like electrostatics, magnetism, gravity, all of those are non-contact forces. Because we're talking about forces, these are vectors. Now, when we come to draw them, because it's a vector, we use an arrow for it. So remember that the direction shows the direction it acts in, the length of it is going to show the size of the actual force itself. If you're drawing a diagram with a non-contact force, then we usually draw those from the center of the object. The contact forces then, these are the ones where the force will only act when the objects are in contact. Again, name kind of suggests it. And we draw those force arrows from the point of contact, so the edge of it, okay? So good examples of this would be friction or drag or upthrust. Any of those are contact forces. Now, for those of you doing the higher tier, you need to know about free body diagrams. So when we're actually looking at a free body diagram, it just shows the forces that act on a single object. Now, what we do is we simplify it. So if they ask you to draw a free body diagram for a football, you don't have to draw this artistic representation of a football. We draw a dot. That's it. And whatever it is, it's a dot or a box. They're your kind of two options here. Now, once we've done that, the next thing is to identify all of the non-contact pairs of forces. Once you've identified the non-contact pairs, you then do the contact pair of forces. And then you're just going to focus on the object it tells you in the question. So if it's talking about a football, we're only concerned with the forces that are acting on the football. So you'll obviously have the two pairs of forces. So you'll have the force of the football on the earth and the force of the earth on the football. But what we need to do is only focus on the ones acting on the football itself. Once you've done that, you then draw your arrows nice and easily, hopefully with a ruler in your exam, and then you're just going to label it. And remember, it's going to be the forces acting on the actual object itself. Still for the higher tier then, you need to know about this thing called a resultant force. Now, the resultant force is just the force we get when two or more forces are added together as vectors. So what we find here is that the direction of it is important at this point. So if we've got a scenario where you've got, just do a quick diagram for you, 5 newtons in one direction and 7 newtons in the other, then what we'll actually do to work out the resultant force is obviously 7 minus 5. So our resultant force in that case is just 2 newtons, because you've got your 7 newtons going one way, 5 newtons the other way. So you just subtract and you've got that last force, that resultant force of 2 newtons. If they're being mean, they could actually give you a question that needs you to use Pythagoras for that. And if you want to see how to do that one, then head on over to the video on the free body diagrams, because I'm not going to go through that tonight for you. Right, back to foundation and the higher tier, then we need to know about Newton's first law. Now, Newton's first law just tells us that any object will continue to stay at rest or move with uniform velocity unless a force acts on it. So in order to actually change the speed or the direction of an object, then a resultant force is required, okay? For those of you doing higher tier, you need to know then that if the resultant force is 0, then the speed or direction of the object doesn't change. So if it's moving, it stays moving at the same speed and in the same direction. If it's not moving, it doesn't move. When we're then talking about this concept of inertia, that's the measure of how difficult it actually is to change an object's velocity. And this is pretty much what Newton's first law is all about. And what we're looking at here is just the fact that moving objects keep moving and stationary objects just don't move. Back to everyone again, foundation and higher, then we need to know about the idea of steady speed. So the speed or direction won't change if that resultant force is zero, which means it's got this steady or constant speed. So do remember those key facts about those terms that we can use there. We could also use this phrase equilibrium, which quite simply is just looking at the resultant force being zero, because the forces in the opposite directions have cancelled each other out. So if you've got an object that's falling at a steady speed, then what we see is it's at equilibrium. Those forces have cancelled each other out. Next one is Newton's second law then, which is just talking about the fact that if the resultant force is not zero, then there's a few things we could see happening here. First one is that we can change the speed of the object. Second, we can change the direction or motion of an object. And then finally, we could change both the speed and the direction. So three things: change of speed, change of direction, or change of both. That basically tells us it is accelerating, because when we're talking about acceleration, that is a change in speed or direction. So for example, an object that's traveling in a circular direction at a steady speed, then that is still accelerating because the direction is changing. So just remember that when we're talking about acceleration, it can be speed or it can be direction. When we think about Newton's second law, then it tells us that the acceleration of the resultant force produces on an object is going to depend on two things. The first is the size of the resultant force. The second is the mass or inertia of the object itself. So this is another equation that we then need to know, one they're not going to give you, which is the force is mass times acceleration. Now, do remember mass in kilograms, and what we're looking at in terms of our acceleration is meters per second squared. So make sure you do know those units. If we're looking at one of the experiments that we could have done on acceleration, then you'd had a little trolley on the desk, which was attached onto some masses that then hung off the end. And obviously what we're looking at there is how it accelerates as the masses then drop to the ground. So what we find here is a couple of things that you should bear in mind. First is that you've got to have a ramp which is slightly raised in order to compensate for friction. Because remember, you'll have friction between the tyres of your vehicle and the surface it's running on. So you raise the ramp until the trolley moves at a steady speed of its own volition. Secondly is to use light gates to record the time, just because it removes that whole reaction time issue that we have with stopwatch and us as human beings. Now, when we actually come on to the next concept, which is terminal velocity, then this is generally associated with skydivers or people jumping off a diving board. They tend to be the two examples that they give you here. So the first thing is when you first jump out of a plane, then the force that's exerted on you by the earth is greater than the force the air exerts on you. So basically there's a greater force pulling you down towards the ground than there is keeping you up away from it. So as a result of that, you're going to accelerate towards the ground. Now, as you accelerate, then what we find is that the force of the air on you is going to increase. So what we find is as you fall faster, the force acting this way is going to increase until eventually they're going to balance out. So that's the point that we've reached terminal velocity, because the force acting down, same as the force acting up. So you're just going to fall at a steady speed all the way down. Now, when you obviously open a parachute, which is always a good idea when skydiving to avoid a rather unpleasant mess on the ground, then what we see is you've got a much larger surface area, and therefore the force of the air is going to increase, which reduces your velocity. So eventually we reach a lower terminal velocity as the forces then balance out once more. Key thing to remember though is that terminal velocity is when the forces are balanced. For those of you doing the higher tier, you do need to know about how we can deal with forces that act at different angles. And basically what we need to do is resolve them so they only act in two directions, which are at right angles to one another. And again, if you want to know more on how to do that, then head on over to my video on the channel on the everyday forces. Everyone again, so foundation and higher, then you do need to think about some of these forces that we use in our everyday lives. Now, a resultant force is able to produce a large acceleration, and a good example of this is in a rocket that's taking off to go up into space. So what we find then is that as we burn the fuel in the rocket, then it pushes gases out of the bottom. So that gas is going to push on the rocket, and the rocket pushes on the gas. Newton's third law, we've got opposites there. And then when the force of the gas on the rocket is greater than the force of the Earth on the rocket, it accelerates and lifts off. So we're just looking at the forces that are interacting, and as soon as we've got one that's greater than the other, obviously the one going up is greater than one coming down, then the rocket comes up. For the higher tier, we need to know about momentum. So momentum then depends on the mass and velocity of an object. So it is going to be a vector quantity in this case, because we are going to be looking at positives and negatives. Now, momentum, another equation you need to know, is mass in kilograms times the velocity in meters per second. So when we're thinking about collisions, then in any collision, momentum is conserved, which is just the law of conservation of momentum. And that just tells us that the momentum before has to be the same as the momentum afterwards. So it's just simply double checking that each side is the same number. If we have an elastic collision, then a collision in which the kinetic energy is conserved is an elastic collision. So that means that our energy in the kinetic store is staying the same. If, however, we're thinking about any typical scenario in everyday life, then this is unlikely, because what we'll actually find is that some energy is going to be transferred to the thermal store by things like the sound that occurs when things collide together. So what we actually have is an inelastic collision, which is quite simply a collision where kinetic energy is not conserved because some of it's been transferred to the other stores. So if we've got sound, then it's inelastic, quite simply. Next thing is for both foundation and higher tier then. So what we're looking at now is work and power. So again, more of these formulas. So work done is measured in joules, which is the force times the distance. And distance should be in meters for this one. Now, work quite simply is the transfer of energy. And what we're actually going to see is that we're going to use forces to transfer energy between different stores. And usually work's going to be done against friction or gravity. The next equation, again, one you need to know, is power. And power is the rate of transfer at which energy occurs. And so the power in watts is the work done divided by the time. Now, what you could find is that they're actually going to give you a question asking you to calculate the power, and all they're going to give you in the question is the force and the distance, and then also your time. So they're not going to explicitly tell you that you've got to do two calculations to get to your final answer. They're going to expect you to work that out. So if they give you that scenario where you've got time, you've got force, you've got distance, and they're asking you to calculate the power, force times distance, first of all, gives us our work done, and then divide that by the time to give you the power in watts. So just remember that you can use more than one calculation to get to your answer in some cases. Now, the next thing we're coming on to is the idea of stretching items. So we've got two key terms we need to know, plastic and elastic. A plastic material is one that won't return to its original shape when we remove the force, whereas an elastic material does return to its original shape. One of the best examples of this is Hooke's law. So you probably did this experiment where you had your clamp stand with a little spring hanging on there, and then you hung the different masses on, measured the length of it. So what we did from that is you then plotted your graph with your weight along the bottom in newtons, and then your extension up the side. Now, what you actually did from that was you plotted a graph of force against extension. And what we see in that scenario is that we actually have a nice straight line to start with. So you have a graph like this, where we start off with that nice straight line that you could draw with a ruler. Now, the key thing about that is that we've got one that's showing a linear relationship. So that initial point, as we increase it by a certain weight, then the extension increases by a certain amount. So it's linear. We then get to this top part here where you can see it actually starts to curve. Now, the reason that we get that is that we've gone past something called the limit of proportionality. So the limit of proportionality is quite simply where the actual linear relationship comes to an end. Now, any spring that you've got has an elastic limit, and depending on how well you listened to your science teacher, you may well have exceeded that elastic limit. So the elastic limit then is below which the spring returns to its original length when you take the masses off. If you took your masses off and your spring was still all stretched out, you'd exceeded it. So beyond the elastic limit, then we say the spring is permanently deformed. So you broke it. Now, in terms of that, we do have another little calculation that we can do, which is looking at our force exerted by a spring. And again, you've got to learn this one too. So the force exerted by a spring is your spring constant times the extension. And if they are being incredibly mean, then they could ask you to work that spring constant out from a graph itself. So if they don't give you the spring constant, but they do give you a graph, all you need to do is work out the gradient of the line here where it's on its nice diagonal, and that is your spring constant. The next thing that you could be asked to do is actually using one from our formula sheet. Okay, so we've got our lovely formula sheet here, which is looking at the energy transferred in stretching, which is 0.5 times the spring constant times your extension squared. So again, it's on your formula sheet, so you can just use that and substitute in your values. Now, what we're actually going to look at next is the idea of gravitational fields and potential energy, so gravitational potential energy. If we talk about a gravitational field, then it's a region where a mass experiences an attractive force. And if we're talking about the gravitational field strength, which is given the little sort of symbol of just a lowercase g, then that's the measure of the force on a 1 kilogram mass when it's in a gravitational field due to another mass. So the mass isn't changing, but the force is going to depend on that field. So this is the idea that a 60 kilogram person on Earth is going to have obviously a weight of 600 newtons, whereas on the moon it's going to be less than that because it's a different gravitational field. The force that acts on an object in a gravitational field will be larger if either the mass is larger or the distance between them is smaller. Another equation for you to learn, I'm afraid, folks, which is that the gravity force is the mass in kilograms times gravitational field strength. Nothing too complicated there. It's literally mass in kilos times g. You also need to know that weight, which is obviously a force, therefore measured in newtons, is the mass in kilograms times gravitational field strength. So they're just different ways they could phrase it. If they ask you to work out the gravity force or the weight, it's the same thing, okay? It's mass times gravitational field strength. Now, our little g can also stand for acceleration due to gravity. So just remember that acceleration due to gravity on Earth is 9.81 meters per second squared, or 10 meters per second squared. When we're actually thinking about lifting an object, so if you've got an object and you raise it off the ground at all, then what we're doing is transferring energy to a gravity store. And that's just called gravitational potential energy. So the GPE, or gravitational potential energy of an object, depends on the object's mass and the height of the object. And that leads us on to yet another equation, which is that GPE is mass times the height times the gravitational field strength. So just remember that all of these equations, they might give you some on the exam paper. They gave you some last year. Foundation, they gave you quite a few, to be honest. Higher tier, I think they only gave you 4 over the entire course, and you used a lot more than just the 4. So you obviously need to learn as many of these as you can before tomorrow. For those of you doing GCSE physics, we need to know about turning forces. So first thing is a couple of keywords. The word pivot, which is the point around which the forces act to produce the turning effects, and the word moment, which is the turning effect of a force. And moments can either be clockwise or anti-clockwise. So clockwise going obviously the same direction that a clock goes in, anti-clockwise going the other way around. Now, the moment itself is going to depend upon the size of the force and the distance from the pivot to the point at which the force acts. So your moment is force times distance, which is something hopefully you remember from Key Stage 3. Now, when we're actually thinking about this principle of moments, then what you are actually looking at is the fact that the force times the distance on one side of the pivot is the same as the force times the distance on the other side of the pivot. So they're going to be the same there. Couple more key terms that we need to know linked into this is a lever, which quite simply is a rod or another object that won't bend that has a pivot. So that when we apply a force on one end, it produces a force in the opposite direction at the other end. So what we're doing is basically using this to transmit a rotational force. So it's kind of the idea that we've got obviously a door handle on the opposite side to the hinges because it's easy to open it. You try and push a door open by pushing close to the hinges, it's not really going to work much because you're far too close. When we're talking about a force multiplier, then this is a factor that's going to greatly increase the effectiveness of a force. And this is why we use a lever. So you want to get a lid off a paint can, you don't just try and lift it up with your thumbnail. You get a screwdriver and then you apply that force onto it. It acts as a lever and we get a much increased force on the other end of it. Now, what we actually find then is that the effort is the force that you're exerting on the lever. The load is the thing you're trying to move. So just be aware of those words so you can identify what's what in an actual diagram. If we're considering the ratio of the load to the effort, then we're looking at something called the mechanical advantage. So in order to work that out, you just do load divided by the effort. So just bear that little calculation in mind in case they ask you it. Another example of where we can see this idea of the forces in action is in simple machines which use gears. Now, what we actually find with gears, which are obviously the little cogs that all tie together, then the ratio of the diameters of the cogs is going to tell you the ratio of the effort and load. So if we've got a cog with twice the diameter of the other one, then the force is going to be multiplied by 2, but the larger cog only moves half the distance of the smaller one. So what we can actually do is we can use those gears to change the direction of a rotating force or the speed at which it rotates. Still just for GCSE physics at this point, you need to know about hydraulics as well. Hopefully you remember that pressure is the force divided by the area, and that if we've got a greater pressure, then we have a greater force. So that if we increase the area of the surface, then what we're going to see there is it's going to have an impact on our actual pressure as well. So this is the idea behind like giant snowshoes versus stiletto heels for walking. Obviously, the changing the area is going to change your pressure. If we think about the hydraulic machines, then these are the ones that use a liquid to transmit a force. So hydraulic jacks, for example, allow you to use a really small force that you can exert to lift something as heavy as a car, for example. So all we're doing there is we're using the liquid to transmit the force between those two. And again, if you want more detail on that, then head on over to the video on my channel on the hydraulics. That is all of P2 done. So next we're on to P3, which is all about the circuits. So if I've got any AQA people kicking around out there, then this is relevant for you guys too. First thing we need to know about then is electrostatics. So when we're talking about electrostatics, we need to know that protons have a positive charge, electrons have a negative charge. There are 3 subatomic particles, which hopefully we learnt in our chemistry: protons, neutrons, and electrons. Protons have a +1 charge and have a mass of 1. Neutrons, no charge and a mass of 1. And the electrons, a -1 charge and a mass of 0.0005. So make sure you know those key facts about them. If they ever ask you why an atom is neutral, it's because they've got the same number of protons and electrons. So the positives and the negatives cancel out. If we think about how we generate a static charge then, what's actually happening is electrons are moving. Now, the key thing here, and the way that people always throw away the marks, is by saying something else moves. The only thing that's moving are the electrons. So what we actually find is if you've got 2 insulators and you rub them together, then electrons get transferred from one insulator to the other. So that means one of the objects is going to have more electrons than protons, and the other has less electrons than protons. So the one that's got more electrons is going to be negatively charged, whereas the one with less electrons than protons is positively charged. And remember, only electrons move. So 2 examples, and you probably actually did this as a practical, where you had little plasticky rods and a duster, and then you tried doing things like bending water, picking up bits of paper and the like. So one of them would have been an acetate rod. So when you rub the acetate rod with the cloth, electrons get transferred from the rod to the cloth. So that means the rod is positively charged and the cloth is negatively charged, because the electrons have obviously gone from the rod to the cloth. If you used a polythene rod, then it's the opposite. So the electrons are being transferred from the cloth to the rod. So the rod is therefore negative and the cloth is positive. So just remember, whichever one is gaining electrons is going to be the negatively charged one. Then we go back to the real basics of opposites attracting. So if you've got a positively charged item and a negatively charged item, then they attract each other. If they're both positive, they repel. If they're both negative, they repel. So just make sure you've gone over the basics on our statics there. If we've got an object connected to a piece of metal, then the charges can flow and therefore the object becomes discharged. So that's one of the ways that we can carry a charge away. Now, we could also discharge an object through a spark. So a spark is just a flow of current through the air, and depending on where that spark is occurring is going to obviously affect whether it's safe or not. So if you're obviously carrying out work cleaning a sort of fuel tanker where you've got these vapors which are quite explosive, sparks would be bad. Whereas if you're obviously somewhere with no flammable anythings, it doesn't matter so much. For those of you doing GCSE physics, you do need to know a little bit more about electrostatics. So where we've got an electric field around a charged object or particle, then placing another charged object into the field is then going to have it either being attracted or repelled. So if we've got another charged object in the electric field, the reason we get that is because the field lines are going to stretch. So the force on an object then is going to be in the same direction that causes the field lines that are going to shorten and straighten. So the closer together the field lines, the stronger that field is, and the direction of the field lines is the direction of the force on a positive charge, remember. For everyone again, so combined foundation higher and the triple foundation and higher, we need to know about electric current. So current, quite simply, is the rate of flow of charged particles, which are the electrons. And in order to make that current flow, you need a cell, a battery, or a power supply. So we also must have a complete circuit here. So if there's any break in the circuit, then obviously current is not going to flow. So just look out if there's a circuit diagram, the gap in it, current doesn't flow, doesn't work. What we then find is that the current anywhere in a single closed loop is going to be the same. Now, when we come on to looking at our current, we come on to our first calculation here, which is charge flow, which is measured in coulombs, is the current in amps times the time in seconds. So what we actually find here is they could give you one of these calculations where they've given you the current, they've given you the time, and they ask you to work out the charge flow. Again, we're multiplying. Now, one of the things that you do need to know are the circuit symbols. And hopefully these are quite familiar to you from Key Stage 3. So you need to know cell, battery, power supply, switch, lamp, ammeters, voltmeters, the resistors, etc. So make sure you can draw them, because they could very well ask you to draw a circuit diagram using any combination of them, because one of your assessed practicals is obviously all to do with circuits. So circuit diagram, perfectly feasible to be a question there. If we're talking about the potential difference then, that's required for the current to flow in a circuit, and it's caused by the separation of charges inside that cell or battery. So basically what we've got is one side being positively charged and the other side is negatively charged. So the positive terminal then has a higher electrical potential than the negative terminal, and we can work out what this potential difference is using our voltmeter, and it's measured then in volts. So when we're drawing it, do remember to actually use quite obvious lines when we come to drawing our cells, our batteries, etc. So we've got one line much longer than the other. Do go careful not to draw them so that they are virtually the same, because if you do that, it's not easy for the examiner to work out which side you're saying is positive and which one is negative. So really exaggerate the difference between it just to be safe. So the positive terminal is the longer of the lines, the negative terminal is the shorter of the lines there. Anytime we apply a potential difference between the ends of a wire, then we've actually got an electrical field being set up within it. Another calculation, next of all then, is your energy transferred, which is the potential difference times the charge. And again, it's one you need to know, I'm afraid. Our next little bit here is looking at the series and parallel circuits. So when we're talking about a cell, first of all, then that is a single, what you refer to as battery. So it's just literally one long line, one short line. Whereas a battery is more than one cell joined together. So just remember that if they're telling you it's a battery, then do two of them. Whereas if it's a cell, that's just one long line, one short line. Now, what we've got here then is a basic series circuit. Now, you can tell it's a series circuit because you can put your finger at the top and you can go round the whole thing without having to lift your finger or go over the same bit twice. It's the easiest way you can identify it. Now, what we actually have is, in our series circuit, the current is the same everywhere. And we can work out what that current is by using an ammeter in our circuit. So you place your ammeter in series. So by series, we put it actually in here, draw your A inside a circle, there it is in series. So ammeter always goes in series. If we wanted to work out the potential difference across any component, then we use our voltmeter, and that goes in parallel, remember. So if we wanted to know the potential difference here, then all we do is we'd extend our lines down and put our voltmeter there in parallel around the component. So make sure that you actually remember that voltmeters are in parallel and our ammeters are in series. So once we've actually connected in our two devices, then what we can do is get our readings. So what we see is that if we were to look at a wire, then connecting our voltmeter across a wire, the drop in potential difference is incredibly low. So in all likelihood, it's going to read 0 on your voltmeter. Whereas you place it across any other component, you get something that's actually a more noticeable reading. What we find then in our series circuit is that the readings on all voltmeters across the components is equal to the reading across the battery. So if we've actually taken a reading across our battery up here, first of all, and then we've taken a reading across this and this, then when we add up these two, it's going to equal this one. Okay, so the readings across all voltmeters in our components will equal the reading in our voltmeter across the battery itself. If we now think about the parallel circuit, then what we find here is that the current in all of the loops add up to the current near the battery. So on our little diagram here, we've got 4 different ammeters, so 1, 2, 3, 4. So what we're actually going to find in this instance is if we add up our 2 and our 3, okay, so ammeter 2 and 3 in those loops, then it's going to be the same as the reading on ammeter 1 and the same as the reading on ammeter 4. So what we find, the current in all the loops adds up to the current near the battery. And the potential difference across each component is the same as across our battery in that case. Now, because circuits is one of those potential assessed practicals they could talk about, then they could actually ask you about how you could go about troubleshooting if your light doesn't light up, for example. Now, one of the things that you'd actually do here is start in that logical progression of hopefully what you did when your circuit didn't work in class. And that's not ask the teacher. That's not a valid answer on your exam. So first thing to do is you connect your bulb to the battery, and if that doesn't work, try another battery. If that doesn't work, try a different bulb. So as soon as you've got your bulb and battery working together, then what you're going to do is just replace a single wire at a time until you've checked all of your wires. So what we then find is that you'll identify which wire is the dodgy one, don't use it, swap it out for another one. Now, when we come on to calculating resistance, then we're going to use our little calculation of potential difference is current times resistance. And they could ask you to rearrange that to either work out the current or the resistance, remember. Now, our current is going to depend upon the potential difference and the resistance in the circuit. Resistance is measured in those units called ohms, which has that weird little kind of alien head symbol. Because current is a dependent variable, then we can only change it by changing the potential difference or the resistance. Now, what we actually find here is we're going to be looking at something called Ohm's law. Quite simply, what that actually tells us then is that current is proportional to the potential difference if the temperature does not change. That's literally what Ohm's law actually is. Next thing is we need to know about our metals. So it goes back to our chemistry knowledge again. So structure of metal, hopefully something we do remember. You've got your positive metal ions and we've got our delocalized electrons scattered around. Now, our metals are all made up of these positive metal ions arranged in that regular pattern, and the outer shell has then lost some of these electrons which have become delocalized. Because they're delocalized, it means they're free to move throughout the structure. What we then get is anytime those delocalized electrons are colliding with the metal ions, we're producing resistance. So it's something that's impeding the flow of those electrons. Now, obviously, what we could actually find is you could be asked about resistance of a wire practical. So if you've got a thinner wire, then what we actually find is it's got greater resistance than a thicker wire because there's just a greater chance of the electrons colliding with the positive metal ions. Same principle applies if it's a longer wire. There's just more chance of those collisions occurring, so resistance goes up. One of the other bits of equipment that you should have used is a variable resistor, which quite simply we use in order to change the actual resistance. So we're changing the amount of current that then can flow through our circuit. And a good example of this is what you actually see in houses in terms of dimmer switches on lights and so forth. So by twisting it, what you're actually doing is you're changing the number of coils of the wire that the current is actually flowing through, and therefore you are changing the resistance. The next thing you need to know about are the graphs of potential difference and current. So what we're looking at are things called a characteristic graph. So all we've done is we've plotted current and potential difference on one graph. Now, obviously, in order to plot those graphs, you need to have actually recorded the potential difference and the current, a range of different values for each component. You then plot it on the graph and obviously draw your lines of best fit. Key thing with this is you need to reverse the connection on your battery or power supply and repeat all of those measurements because you need both positive and negative values for this. The first one we've got then are the linear circuit elements. So linear circuit elements then are the components that have a resistance that doesn't change. So this would be things like your fixed resistor, for example, given a really obvious diagonal line. So that one is one of our linear circuit elements. If we've got a non-linear circuit element, then this has a resistance that will change. So something like a lamp, for example. So you can see it's actually got a very different shape on the line to it. And what we actually find then is that as the electrons collide with the metal ions in the wire, the ions vibrate more. That means that the wire gets hotter and we then get that change in the actual resistance overall. So do bear in mind linear and non-linear. Our next thing we need to know about is a diode. Now, diodes have this very distinctive little sort of horizontal line and then it goes up. Now, the reason for that is that a diode will only let current flow one way. There are some that emit light called light emitting diodes or LEDs. And what we actually find is that when you're looking at the diode itself, the long leg of it connects to the positive terminal, just as a random little one marker they could ask you. Now, what we find then is that as the potential difference is applied in the forward direction, we get very little current flowing initially and then a rapid increase. And if we reverse the potential difference, because diodes only let the current flow in one direction, then no current will flow. Hence why we just get it running along our actual base axis. Second one is our thermistor, which is basically a kind of resistor that responds to changes in temperature. So what we then find is that it's made of a material called a semiconductor. And the most common example of this is silicon. So that what we actually find then is that the electrons that are present in those silicon atoms don't need much energy in order to actually escape to form this current. So as we heat up our thermistor, the electrons gain enough energy to escape from the atoms in the semiconductor, and therefore the resistance is going to drop. So what you then get is a very distinctive graph where you can see it drops, so that as we're looking at our increase in temperature, there we go, then the resistance is decreasing. So at low temperatures, we've got a small current and therefore high resistance. At high temperatures, the current is high, the resistance is low. The last one that we're going to look at then is the LDR, or light dependent resistor. So this is a resistor that responds to changes in light intensity. And again, it's made of a semiconductor. Now, light then is going to cause the electrons to be released and therefore to increase the current. So as the light intensity increases, more electrons are released, and the semiconductor is then going to release those electrons with the resistance decreasing. So light level along the bottom, as the light level increases, then the resistance decreases. Same thing. Now, what we then need to come on to are the calculations of net resistance. So what we actually find is net resistance is the resistance of a circuit if all of the components were replaced with a single resistor. And what we find is the net resistance will change if the components or their arrangement is changed at the end of the day. So if we consider an identical lamp added in series, then the current will decrease and the net resistance will increase. If we were to add an identical lamp in parallel in our circuit, then the total current increases and the net resistance decreases. There's a few things we should remember here, because there's a couple of key facts that are going to help us out an awful lot here. First of all, if we think about our series circuit, then the current is the same everywhere, and the potential difference across each component adds up to the potential difference across the battery. And then we know that V equals IR. Okay, so just going back to potential difference is current times resistance. If you remember those three facts, then you can go on to carry out a whole range of calculations to do with it. For our parallel circuit, the potential difference is the same across each of the loops, and the current in each loop adds up to the current near the battery. And again, potential difference is current times resistance. So if you've learned those facts about series and parallel, then you can actually work out a range of different calculations depending on what they give you. And if you want to know more about how to do those calculations, again, head over to the net resistance and circuit calculations video on the channel. Very last thing to consider are sensing circuits, which are basically where we're using some of these thermistors and LDRs in order to actually control a circuit for some purpose. So we could use an LDR to monitor the light levels in a greenhouse and therefore turn lights on when we need it to. We can use a variable resistor to monitor the position of a door to actually change how much it turns. We can use pressure sensors in burglar alarms. There's a whole range of different ways we can use these sensors to then trigger some kind of a response. Very last bit of P3 then is looking at power, which is the rate of transfer of energy measured in watts, as we've already established. And we've got another way that we can work this out. So power is potential difference times current, but it could also be used in our energy transferred is power times time, which could obviously be rearranged. Now, you do need to learn the formulas for those, and there is no quick way to do it. If you've not learned them already, then obviously try and learn as many as you can before tomorrow's exam, because there are going to be calculations. We know this on physics. They are not necessarily going to give you any of these calculations on the paper itself. They will give you the information and expect you to recall the formula and therefore use it. Now, the last little bit for those of you doing combined is a little bit on magnets. For those of you doing triple, this is now P4 for you. So when we come on to consider magnets, if we've got two bar magnets and we push them together, like poles repel, opposite poles attract. So that's basics we learned back in year 7. If we're talking about field lines, then what we actually have are those lines represent something called magnetic flux. And the number of the field lines passing through a particular area is the magnetic flux density, or you might refer to it as the magnetic field strength. Now, obviously, if you've got lots of those lines, then it's got a high magnetic field strength or magnetic flux density. There's only a few, it's low. What we then find is that if we've got magnets interacting, then they move in the direction that makes those field lines shorten. We've got two types of magnet. There are permanent magnets and we've got induced magnets. So a permanent magnet is one when there are no other magnets around or a current is removed, it remains magnetic. Whereas an induced magnet is one where we're only going to have that magnetic effect when a magnetic material is placed in a magnetic field. And if you remove that magnetic field, it may not remain magnetic at all. One of these ideas that we use to try and explain this is called the domain model of magnetism. And this just tells us that a permanent magnet is made up of many small magnetic regions called domains that all line up. So if we think about iron and steel, then we've got regions that aren't lined up. But when we place them inside a magnetic field, they do line up, and therefore they become magnetic at that point. In some magnetic materials, then the domains remain lined up when we've removed the magnet. In others, the domains return to their original direction, and therefore it's no longer magnetic at that point. If we actually think about compasses, then they point towards magnetic north. So what we find here is it's not the same as the North Pole, it's pointing towards the magnetic North Pole, which is a little bit off. And the reason for this is that the Earth behaves basically like we've got a giant bar magnet at the center. And what we actually think is that the Earth's magnetic field is caused by these convection currents that are occurring within that molten iron core of the Earth, which then means when you're holding a compass, it's going to point to magnetic north then. The next thing we need to understand are the currents we've got in our magnetic fields. Now, what we find here is that when we've got a current flowing through a wire, we have a magnetic field around it. So if we just have a single piece of wire, so if it's basically our piece of wire like this, then what we can do is use your right hand. Hopefully you know the difference between left and right. So you're going to hold this in the same direction. So the way your fingers wrap around is pointing the same direction that we've actually got our current flowing, okay? It's not our current flowing, sorry. That's going to be the direction of the magnetic field lines. Your thumb is going to be pointing the direction the current is going. So if in this piece of wire the current is flowing up, then you'd hold it like that. Current, obviously, is then going around in this direction. If it was flowing that way, then our magnetic field lines are going the other way. Last year, I do believe that they actually asked a question to do with drawing a diagram to show the magnetic field lines around a single wire. So all you're looking for are concentric circles at that point. So right hand for a single piece of wire. Now, what we actually find is to show a wire producing a magnetic field when a current flows through it, then you need to, first of all, connect the wire into a circuit with a cell and a switch in it, place a compass under that wire, and then when you actually press the switch and the current flows around, the compass then aligns with the field produced. So that's how you can demonstrate this if they ask you that question. If we think about the actual strength of that field, then we're looking at the magnetic flux strength. And it's going to depend on two things. First one is the magnitude of the current. So the bigger it is, the stronger it is. And the second one is the distance from the wire. So the closer, the stronger. Now, what we find is when we're talking about the strength of a magnetic field, then it's measured in Teslas, which is given the symbol of a capital T. When the current is passing through a loop of wire, then the magnetic field in the center is actually just a straight line. So if you've just got a piece of card with a loop of wire running through it, then down the very center, it runs as a straight line. The others run in those concentric circles around both sides. If we're talking about something called a solenoid, then that's where we've got a coil of wire. And what we find is that having lots of loops in this coil is going to make a stronger field here. If you wanted to increase the strength of it further, then inside that coil, you can place a magnetic material. And that's the principle of those electromagnets that you've probably heard about back in Key Stage 3. Because when we've actually placed that magnetic material within the coil of wire, what we're going to do is create an induced magnet in that magnetic material as the current flows through. So we've increased the strength of our magnetic field at that point. And the electromagnets that we can make are actually much stronger than any permanent magnet. And a really good example of that are the MRI scanners that we use. For those of you doing higher tier then, what we need to know about are what happens when we actually combine fields. So if we've got a current carrying wire and we place it inside another magnetic field, then those two magnetic fields are going to interact with one another. So what we find is the two magnetic fields push on each other and they're going to create a force on that wire. So the force on the wire is always at right angles to the magnetic field. So that if we've got two fields in the same direction being put together, then they add up. If they're in the opposite direction to each other, they cancel out. When we then come to look at this, what we're looking at in most cases is something called a catapult field. So with our catapult field then, what you've actually got is the idea that your wire is pushing the magnetic field lines out of line. Now, we've actually got fewer stretch lines below than we do above. So as a result of that, because those field lines want to shorten, they push down and therefore the wire moves down, because that motion is going to shorten the field lines, which is the end goal. Which brings us really nicely onto Fleming's left-hand rule. So again, hopefully we know the difference between our left and our right hands. If not, then you can always just do that, 8 and L for the left. And this is where you are actually allowed to make weird hand gestures in an exam. Hopefully your science team have told the invigilators you're not signaling to each other, you're just trying to do this weird little sign here. Now, Fleming's left-hand rule relies on your thumb, your first finger, and your second finger. So what we actually find is your first finger is going to point from north to south. So whichever way north to south is on the magnet, that's the way it points. Your second finger here is your current. So that's going to point the direction the current is moving in, which is usually into the paper or out of the paper. And then your thumb tells you the direction of the movement. So usually on your exams, it will either be up or down. So all you need to do is get your hand set up in this weird little finger gun. You then put your finger here facing from north to south, so pointing in that direction. Your second finger, you then make sure it's either pointing out at you if the current is flowing towards you, or you flip it the other way if it's going into the paper, and then you just look at the thumb. In that case, it moves down. In this case, it moves up. So that's literally how we can work out the direction that it moves. Now, when we're considering the forces that are going to act on these actual items, there's another calculation here. Good news, they give it to you. You don't have to learn it. It's on your formula sheet. So your force on a conductor carrying a current is the magnetic flux density times the current times the length. You'll know north and south on the actual exam question because they will label north and south on the magnets. So you don't have to try and work it out. You can literally just look and point from north to south. The size of our actual force on a conductor carrying a current is going to depend on the current, the length, and the strength of that field. So just remember that that is again on your formula sheet for you to use. One of the ways they could actually ask you to utilize this knowledge is when we're talking about motors. Now, if we just place a loop of wire inside a magnetic field, then what we find is that the force that's generated on two sides of that loop are going to actually make it turn. So what we end up with here is your simple motor. So here's your coil of wire, there's your magnetic field. And because obviously the current is flowing in one direction, so it's going into paper there and out here, then we see this side moves down and that side moves up. So as a result of that, the whole thing then spins. So we're just turning it in that instance due to the interaction of those forces. Now, in order to actually make that so it spins continuously, which is what we want in a motor, then what we need is the current to always be going in the same direction on the left and the same direction on the right. It can't swap over. Otherwise, literally, it would just kind of vibrate backwards and forwards. And the way we do that is through using something called a split ring commutator. So your split ring commutator is this little thing here. So it's called a split ring because, as you can see, it's got a split in it. Now, that's then going to allow the current to flow the same way from the battery, but it changes halves of the coil as it spins. So that means that the force on the left of your coil is always up and the force on the right of the coil is always down, for example. So that means that as it turns, then it keeps turning that same way, because anytime we've got a force acting on this side, it's always up. Anytime on that side, always down. So it just keeps spinning it round and round. Now, if we wanted to change the speed of our motor, there's a few ways we could do that. First one is we could increase the size or the magnitude of the current. Second one is that you could increase the strength of the magnetic field. Third one is we can increase the number of coils in the wire, or we could increase the actual length of the coil itself. So you've got 4 things we could do there. What you need to do, though, is just have a little look at the question. Because if it says, how can you increase the speed of a motor, then obviously you need to say, make the current larger. You can increase the strength of the magnetic field. If they're asking you how you can increase the speed of a motor and you just say, change the size of the current, it's not enough. You're not going to get the marks there. So be specific. For those of you doing the GCSE combined science, then that's it. There's nothing else for you now. The last bits are only for those of you doing triple science. So for those of you doing the triple science higher tier paper, then what you need to know about is electromagnetic induction. So this is the idea that if you move a wire in a magnetic field so that it's cutting those field lines, then we're going to have an induced potential difference being produced across that wire. Now, we can also achieve that by making a magnetic field change around the conductor. But the key thing here is that if the wire doesn't cut the field lines, then no induced potential difference is going to be produced. So the key thing is that we've got to have field lines being cut. 3 ways that we can increase the induced potential difference. 1, move the wire faster, cuts more field lines. 2 is we can use a stronger magnetic field, therefore there are more field lines, and so it will cut more of them. And the third one is use more wire or more coils on the wire. So what we're actually looking at here then is if you connect the wire to a circuit, then a current is going to flow. We know that. When the current flows in a conductor, we produce a magnetic field. We know that. If the wire is in a magnetic field, a force is going to act on it. Again, stuff we already know. If the magnetic field produced is in the opposite direction to the field that produces the potential difference in the wire, then we're going to start to see something else. Now, when we actually have an example here, which is a great little trick you can do with people, if you've got a metal pipe and you drop a magnet through it, then get people to try and catch it at the bottom, because they'll expect it to fall straight through, and it doesn't. Because as the magnet is actually passing down that metal pipe, it's inducing a current in the pipe itself. As we've induced the current, then we're producing a magnetic field. We've then got a magnetic field in a magnetic field. And because the direction of the current opposed the change in the magnet's field, it repels the magnet and it falls really slowly. So you can win yourself a few quick quid just by literally getting people to try and catch a magnet at the bottom and betting they can't if you really want to. Probably don't do that at school though. Next thing we need to know about are generators then. So the first thing we're going to look at is an alternator. So in an alternator, then we've got a coil of wire spinning between the poles of a magnet. Now that's going to generate an alternating potential difference as the potential difference is changing direction, hence alternating. The brushes that we've actually got in our alternator then aren't actually physically attached to the slip rings. Okay, they're not like glued on or anything. They always just brush against them, so the circuit is always connected, but the coil's not tangling. So this is our setup for our alternator. There's our coil, here's our magnetic field, and then we've got our little slip rings here. So this allows it to spin without tangling. The next thing we've got is something called a dynamo, which is going to generate a direct current, or DC. Now, the potential difference that drives a current doesn't change direction. So this is using a split ring commutator. So we've already looked at the split ring, it's the kind of 2 halves. Because the direction of the potential difference isn't changing, because the coil is connected onto this split ring commutator, then what we find is it's always above the line, it's always in the positive on our graph. However, the magnitude is going to change. So direction doesn't change, magnitude does change in our dynamo. If we wanted to increase the output of either a dynamo or an alternator, same things, use a stronger magnetic field, use more turns in the coil, spin it faster. You'll see a repeating pattern coming through these videos now. If we then want to look at transformers, which is still just for the GCSE physics higher tier folks, then a transformer is going to either increase or decrease the potential difference. So what we actually find here then is that the potential difference is induced when the magnetic field lines cutting the coil change. So we can change the field lines that are being cut in 3 ways. First one is we can actually move a magnet or the coil. Either one moves, it's going to cut lines. Second, we can use another coil and then turn the current in it on or off. Or thirdly, we can use another coil with an alternating current. So there's 3 things that we can actually do there to change the number of field lines that we're cutting. Now, when a current is going to flow, we know it produces a magnetic field. So that if the coil is turned on or off, we're clearly changing the number of field lines that are cutting across the second coil. If we use an alternating current, the reason that works is because the field lines are constantly changing. Remember, they're going positive, negative, because they're changing direction. So we're again seeing that constant change. Now, when we look at what our transformer looks like, it's quite simply an iron core, and then we've got coils of wire around the 2 sides. So we've got our primary coil and our secondary coil. The key thing about our transformers is, first of all, that core is made of a magnetic material. And secondly, the number of turns on the primary compared to the secondary coils. So what we find is the magnetic field is actually trapped inside that iron core. As we get an alternating potential difference across our primary coil, we produce an alternating current in that primary coil. So that what we then end up creating as a result of the alternating current in the primary coil is a magnetic field in the iron core that is constantly changing, because if the current is alternating, then our magnetic field is changing. As a result of that, we then induce a changing potential difference in the secondary coil. So just by having our current flowing into our primary, we're then getting this change in our secondary. 2 types of transformer you need to know about: step up and step down. Step up transformers increase the potential difference, and the way they do that is by having more turns on the secondary compared to the primary coil. And a step down transformer decreases potential difference by having more turns on the primary compared to the secondary. For those of you doing GCSE physics, both foundation and higher, you need to know about loudspeakers and microphones, which is our last thing for the night. So a microphone then, the one we're going to talk about, is a dynamic microphone. Now these work kind of like a generator. Sound waves themselves are pressure waves, and we're going to look at that in our next physics seminar. Now, the pressure wave is going to hit this item called a diaphragm. Now, in our microphone, there's basically this membrane, which is the diaphragm, and as that pressure wave hits it, it's going to move it. So what we end up with are these compressions, which are the areas of high pressure, push the diaphragm in, and the rarefactions, the areas of low pressure, pull it back out again. So you end up with this sequence where it just pushes it in and out. Now, as it moves in and out, so this is our diaphragm, there's our sound wave coming in. As it pushes it in, then what we can see is our coil of wire is going to move over the magnet. So as it moves in, then it moves across the magnet and then back out again. So what we then see is, as a result of that pressure wave hitting the diaphragm, moving it in and out, then the coil moves in and out too. So we induce a potential difference across the ends of the wire, and that electrical signal is what the microphone can then produce. We do have another type of microphone called a carbon microphone, which is where we've got these little carbon granules behind the diaphragm, so that as the sound wave hits the diaphragm, it changes the resistance of the carbon, and a current passing through the carbon granules will change as their resistance changes, again allowing us to generate that electrical signal. Very last thing we need to know is our loudspeaker, which basically acts like a motor. So you can actually do this by having your kind of same setup, a big cone of paper, a piece of wire, and a pair of magnets if you wanted to build one. If you connect the ends of the wire to a changing potential difference of a suitable frequency, you will hear a sound. And by changing the potential difference, we're producing a changing current. And in turn, that produces a force on the coil of wire because it's in a magnetic field again. So that means the code is going to move in and out, and that's then going to create that difference in the pressure. So you're going to get the compressions, the rarefactions, we're creating a sound wave, which is what you can then hear. And remember that the movement of that coil is going to depend on the size of the potential difference. And that is all of your P4 stuff as well. So hopefully that's helped to just refresh some of those bits in your mind. As I've said before, if obviously there are some of those bits you're still not 100% sure on, then there are the playlists on the channel. Go and have a little look at them. And any of the calculation bits, there are videos on those with the worked examples to take you through. So make sure that you do know, first of all, the formulae that they're not going to give you on the exam paper. And make sure that when you're using them, write the formula first, then substitute in, and then type it into your calculator and write the answer on the answer line. Because the trouble is, if you literally just type it into your calculator and write the answer down with no working, and you've made a silly error on the calculator, you've got no marks at all. At least you would get some of your marks before you got to that point. So hopefully you found it useful, and we will be doing the live streams after half term for the paper 2s. Now, I will decide a bit later on whether I'm actually going to bother having the chat going, because I don't really think that you're benefiting from it other than people coming in and just posting a whole load of rubbish, to be perfectly fair. So we probably won't have the chat running on those ones so that people can come along, you can revise, but you won't have the opportunity to ask any questions at that point. So good luck for your exam tomorrow. Remember, calculators are key for a physics exam because there's an awful lot of calculations on there. So good luck tomorrow.